April 8, 1945. Pearl Harbor, Hawaii. Commander Edmund B. Taylor climbs aboard a seaplane bound for Okinawa carrying nothing but cameras, measuring instruments, and authorization from Admiral Nimitz to examine something no American has ever seen. The wreck of Battleship Yamato, lying in 1,100 feet of water. The Americans had sunk her yesterday with 19 torpedo and 17 bomb hits in a 6-hour aerial assault that killed 2,498 Japanese sailors. Standard doctrine said any capital ship taking that much damage would sink. But Yamato wasn't supposed to be a standard ship. Japanese propaganda called her unsinkable. Intelligence reports described torpedo protection systems more sophisticated than anything American battleships carried. Taylor's mission: understand how the most heavily armored battleship in history, carrying 22,500 tons of armor plate, more than some destroyers weighed complete, went down so quickly. The preliminary damage reports troubled him. Yamato took most hits on her port side, gradually listing until she capsized and exploded. A ship with 1,147 watertight compartments and 5.1 meters of torpedo bulges shouldn't flood that fast. Something was wrong. What Taylor would discover in the wreckage would shock naval architects worldwide. The impossible protection system worked exactly as designed, but a single structural flaw, hidden below the waterline where nobody looked during construction, turned engineering brilliance into catastrophic failure. Before we reveal how one welding decision doomed Japan's super battleship, annihilate that subscribe button. Like this video and comment which WW2 warship amazes you most. This channel exposes the engineering secrets that determined who won at sea. Now let me show you why Yamato's impenetrable armor was actually a time bomb. November 4, 1937. Kure Naval Arsenal, Japan. Chief Naval Constructor Keiji Fukuda stands before a scale model of what will become the largest battleship ever built. The model sits on a table in a locked room where only 20 men in the entire Imperial Japanese Navy have clearance to enter. The project carries the code designation No. 1 battleship and represents Japan's answer to an impossible strategic problem: how to fight a numerically superior American fleet. The Washington Naval Treaty of 1922 limited battleship construction by tonnage, giving America a 5:3 advantage over Japan. The treaty expired in 1936. Freeing Japan to build without restriction. But industrial capacity remained the hard constraint. America could outbuild Japan in virtually every category: steel production, shipyard capacity, trained workforce. If war came, Japan would face perhaps 20 American battleships with maybe 10 of their own. The mathematics were catastrophic. Fukuda's solution was radical. Build fewer ships, but make each one so overwhelmingly powerful that it could defeat multiple opponents. Not a 1:1 exchange, but 1:2 or even 1:3. The Americans were building battleships designed around 16-inch guns, already massive weapons. Fukuda proposed 18.1-inch guns, the largest ever mounted on a warship. 9 of them in 3 triple turrets. Each shell would weigh 1,460 kilograms and could penetrate any armor the Americans could build. But massive guns meant massive armor to protect against equivalent weapons. And massive armor meant massive weight. Fukuda calculated that achieving the desired protection level would produce a battleship displacing approximately 72,000 tons fully loaded, 50% heavier than any existing warship. The engineering challenges were staggering. The armor scheme Fukuda designed was unprecedented. The main belt, the vertical armor protecting the hull, would be 410 millimeters thick, forged from a new alloy called Vickers hardened steel that Japan had developed through captured British technology and indigenous metallurgy. This belt extended 6 meters deep, far below the waterline to protect against underwater shell impacts. Beneath the main belt, Fukuda designed the anti-torpedo system. This was where Yamato would theoretically become unsinkable. The system consisted of multiple layers extending 5.1 meters inboard from the hull's outer skin. The first layer was a 60 millimeters thick bulkhead, designed to rupture and absorb initial blast energy. Behind that, a void space, an empty gap filled only with air. Behind the void, fuel oil tanks. Oil, being liquid, would absorb shock and disperse explosion energy. Behind the fuel tanks, another void. Then a 50 millimeters armor bulkhead. Then another void. Finally, the holding bulkhead, the last defense, a 200mm armored barrier protecting the ship's vitals. This layered defense system meant a torpedo would need to blast through 5 separate barriers, each designed to reduce its destructive power incrementally. Japanese engineers calculated that even a 400 kilograms warhead, larger than any torpedo currently in service, would exhaust itself before reaching the ship's machinery spaces. The system represented the most sophisticated underwater protection ever attempted. But there was a fundamental engineering challenge that Fukuda couldn't fully solve: the junction point. The armor scheme divided into 2 main belts, the upper belt covering the freeboard above water, and the lower belt extending below. These belts met approximately at the waterline, and they had to connect somehow. This joint represented a structural discontinuity, a place where 2 massive armor plates met under different load conditions. Fukuda's design called for a stepped connection, the lower belt overlapping behind the upper belt with a complex series of backing plates and rivets. In theory, this distributed stress across multiple connection points. In practice, it created a seam that behaved differently than the continuous armor on either side. The upper belt was designed for shell impact, violent, instantaneous shock from projectiles striking at high velocity. The lower belt was designed for water pressure, constant, distributed loading. Where they met, both types of stress converged. Japanese metallurgists developed the VH armor through a process involving nickel-chromium alloys and surface hardening that created plates with exceptional resistance to penetration. But the hardening process made the steel brittle, excellent for defeating shells, problematic for withstanding flexing stress. A shell hitting solid armor would shatter against a plate that refused to deform. But repeated stress at a joint, where plates flexed slightly with wave action and hull movement, could propagate cracks through the brittle material. Fukuda was aware of this tension between hardness and toughness. His solution was to specify that the junction zone receive special treatment: annealing to reduce brittleness, additional backing plates for reinforcement, and careful inspection during construction. The design specifications were explicit. Junction between upper and lower armor belts requires Class A inspection with particular attention to weld integrity and backing plate alignment. Construction began in November 1937 at Kure Naval Arsenal's newly expanded No. 1 drydock. The project proceeded under extreme secrecy. Workers signed documents acknowledging that discussing any aspect of the construction outside the yard was treason punishable by death. The yard established a separate entrance for Yamato workers, preventing contact with personnel building conventional warships. The armor installation consumed 2 years. Each plate had to be precisely shaped, heated, positioned, and secured. The largest plates weighed over 90 tons, requiring specialized cranes and handling equipment. Positioning the lower belt armor underwater while maintaining the correct angle and ensuring proper overlap with the upper belt was extraordinarily difficult. In May 1939, workers began installing the armor belt junction. The upper plates went on first, followed by the backing structure, then the lower plates. The riveting crew worked from scaffolding built inside the hull, driving heated rivets through pre-drilled holes. Each rivet had to be perfectly set. Too loose and the joint would have gaps. Too tight and the metal might crack. Here's where the fatal error occurred, though nobody recognized it at the time. The lower belt's backing plates, which should have extended fully behind the junction zone to provide continuous support, ended approximately 30 centimeters short of the design specification. The installation supervisor, overwhelmed by the complexity of fitting curved armor plates to a curved hull while maintaining precise tolerances, made a field decision: slightly reduce the backing plate length to ease installation. The visible portion of the joint looked perfect, rivets aligned, plates flush. But internally, a 30-centimeter gap meant the junction's load path was discontinuous. The inspection team never caught it. They measured the visible rivets, checked the plate alignment, verified the surface finish, all perfect. But the backing plates were hidden behind the outer armor, accessible only during installation. Once the outer plates went on, inspecting the backing structure became impossible without disassembling everything. The inspection checklist included verify backing plate installation, but this was interpreted as checking that backing plates existed, not measuring whether they extended to specification. The supervisor who made the decision, Master Shipwright Takashi Yamamoto, was 58 years old and had built warships for 35 years. He understood that construction always involved compromise between design ideals and physical reality. The 30-centimeter gap seemed minor compared to the overall junction structure. The joint still had massive strength, just not quite what the designers intended. Yamamoto made a note in his personal log but didn't escalate it to engineering review. The schedule was aggressive, the pressure intense. Reporting a deviation would trigger investigations, delays, potential blame. The joint looked solid. It would hold. Yamato was launched on August 8, 1940. Workers had installed 22,500 tons of armor, more than the entire displacement of many cruisers. The ship represented the pinnacle of Japanese naval engineering, and everything visible suggested perfection. Sea trials in October 1941 revealed a battleship that exceeded design specifications in most areas. The guns were accurate. The engines delivered 150,000 horsepower. Speed trials showed 27.5 knots, respectable for a 72,000-ton vessel. The underwater protection system never received a full-scale test. You don't deliberately torpedo your own battleship to verify the system works. Instead, engineers relied on calculations, scale models, and confidence in the design mathematics. Smaller test sections had been subjected to explosive charges in controlled conditions, and those results matched predictions. The layered defense theory was sound. December 16, 1941. Yamato commissioned into the combined fleet as flagship. 9 days after Pearl Harbor, she represented Japan's ultimate naval weapon, but she wouldn't see combat for over 2 years. Admiral Yamamoto Isoroku, commanding the combined fleet, recognized that Yamato was irreplaceable. Losing her would be a strategic catastrophe. Better to preserve her for the decisive battle doctrine that guided Japanese naval thinking. The single massive engagement where the combined fleet would annihilate American forces in one stroke. So Yamato spent 1942 and 1943 at Truk Lagoon, occasionally sortying but never engaging. Her crew trained constantly, maintaining readiness for a battle that never came. Meanwhile, the war turned against Japan. Midway decimated the carrier fleet. Guadalcanal bled resources. The Solomon Islands campaign exhausted Japan's ability to sustain forward operations. By late 1944, the strategic situation was desperate. October 1944. The Battle of Leyte Gulf. Yamato finally enters combat as part of Admiral Kurita's center force, attempting to destroy American invasion shipping in the Philippines. During the approach, submarines and aircraft attack the Japanese fleet. Yamato takes 2 bomb hits that penetrate her upper deck but cause relatively minor damage. Her armor performs as designed against aerial bombs. The thick plates simply absorb impacts that would cripple lesser ships. But Yamato never closes with American surface forces. Kurita, shocked by the ferocity of American air attacks and confused by contradictory intelligence, orders retreat before Yamato's guns engage their intended targets. The battleship that was supposed to decide the war fires her main guns just once, at aircraft too far away for effective engagement. The Leyte Gulf operation reveals a crucial reality. Yamato's weapons are irrelevant if she can't reach the enemy. American carriers can launch strikes from 200 miles away. Yamato's 18.1-inch guns have maximum range of 26 miles. She's a sword in a gunfight, imposing up close, useless at the ranges modern naval warfare actually occurs. April 6, 1945. Operation Tengo. Japan's final desperate gamble. American forces have invaded Okinawa, bringing the war to Japan's doorstep. The Imperial Navy has perhaps 200,000 tons of fuel oil remaining, enough for one last sortie but not enough for sustained operations. Admiral Toyota Somu issues the order. Yamato will beach herself on Okinawa's shore and use her massive guns as stationary artillery supporting Japanese ground forces until she's destroyed. It's a suicide mission disguised as strategy. Everyone involved understands Yamato won't survive the journey. American carriers control the sea approaches completely. But dying gloriously serves a purpose, tying down American aircraft that might otherwise support ground operations, demonstrating Japanese willingness to fight to extinction, perhaps encouraging better surrender terms. Yamato departs Tokuyama anchorage at 1,520 hours on April 6, accompanied by light cruiser Yahagi and 8 destroyers. No air cover. Japan's remaining aircraft are reserved for kamikaze attacks. The fleet carries only enough fuel for a one-way voyage. Captain Kosaku Aruga addresses the crew. "We will fight until we are destroyed. Let us make our deaths meaningful." American submarines spot the Japanese force almost immediately. Threadfin and Hackleback shadow the formation throughout the night, radiating position reports. By dawn on April 7th, Admiral Mark Mitcher's Task Force 58 has positioned 5 fleet carriers and 6 light carriers within striking range. He launches 386 aircraft at 1,000 hours, the largest single strike the Pacific War has yet seen. Yamato faces nearly 400 aircraft alone. The attacks begin at 1,232 hours. The first wave comes from the south, torpedo bombers from USS Bennington and Hornet, approaching low across the water. Yamato's anti-aircraft batteries open fire at maximum range. The sky fills with tracer fire and shell bursts, but American pilots push through. The first torpedo hits Yamato's port side at 12:37, striking amidships near frame 150, directly in the zone where her underwater protection system should perform optimally. The torpedo, a Mark 13 carrying 600 pounds of Torpex explosive, roughly 275 kilograms TNT equivalent, detonates against the outer hull. The blast wave propagates exactly as Fukuda's design anticipated. The first bulkhead ruptures, absorbing initial energy. The void space contains the expanding gases. The fuel oil tanks compress, dissipating shock. Everything works as designed until the blast wave reaches the armor belt junction. Here's where physics meets the 30-centimeter backing plate gap. The explosion creates stress that should distribute across the full junction structure. But the missing backing plate means stress concentrates at the unsupported edge. The brittle VH armor at the junction, designed to resist shell impact but vulnerable to repeated flexing, cracks along the rivet line. Not a small crack, a fracture that propagates 6 meters vertically within seconds. Water floods inward not through the controlled damage zone Fukuda designed, but through a rupture that bypasses 3 layers of protection simultaneously. The holding bulkhead, never meant to face direct blast pressure, fails. Water cascades into 6 compartments at once. Yamato develops a 5-degree port list within 90 seconds of the first hit. Damage control teams respond immediately, closing watertight doors and activating pumps. But they're fighting flooding that shouldn't exist. The design anticipated isolated compartment flooding, manageable through counterflooding on the opposite side to correct list. This is different, multiple adjacent compartments flooding simultaneously through a single breach that compromised structural integrity. The second torpedo strikes at 12:40, also port side, forward near frame 110. The pattern repeats: explosion, stress wave, junction failure, catastrophic flooding. Another 6-meter crack. 8 more compartments flooded. List increases to 10 degrees. The third hit at 12:42 near frame 170. Same result. By this point, engineers monitoring damage from the central command station recognize something is fundamentally wrong. The flooding rate exceeds anything the damage control doctrine accounts for. Captain Aruga orders counterflooding on the starboard side to correct the list. This is standard procedure: deliberately flood compartments on the high side to level the ship and improve stability. But counterflooding only works if you're not already flooding uncontrollably on the damaged side. Yamato's crew opens seacocks, admitting thousands of tons of water that temporarily reduces list to 6 degrees. But at the cost of overall buoyancy, the ship settles deeper in the water. The 4th torpedo, 5th, 6th, each hit produces the same junction failure. American torpedo bombers are targeting the port side specifically, standard doctrine to concentrate flooding and induce list. They don't know about the structural flaw, but they're exploiting it perfectly. By 12:50, Yamato has taken 8 torpedo hits. Her port side below the waterline is effectively gutted. Dozens of compartments flooded, armor belt junction cracked in multiple locations, list reaching 15 degrees despite counterflooding. The crew struggles against physics. Pumps move 400 tons of water per hour, impressive capacity that means nothing when you're admitting 2,000 tons per hour through massive ruptures. Damage control parties wade through knee-deep water trying to shore bulkheads that weren't designed to hold back sea pressure from adjacent flooded compartments. Men are trapped in compartments when watertight doors seal automatically. The intercom carries reports of flooding in sections that shouldn't be flooding. evidence that water is propagating beyond the damaged zones through cracks in the supposedly watertight structure. The 9th and 10th torpedoes strike within seconds of each other at 13:02. The port list increases to 20 degrees. Yamato's massive weight and low center of gravity have kept her upright despite incredible damage. But there are limits. At 20 degrees, loose equipment begins sliding. Shell hoists jam. Men struggle to stand on sloping decks. Captain Aruga orders all hands topside. Staying below risks being trapped when the ship capsizes. By 13:30, Yamato has absorbed at least 12 torpedo hits. American aviators report she's visibly lower in the water, listing heavily to port, but still under power and maneuvering. This seems impossible. 12 torpedoes should have sunk any battleship afloat. But Yamato's sheer size and compartmentalization mean she retains buoyancy even with catastrophic damage. What the Americans can't see is that the underwater armor belt junction has failed in at least 15 locations, creating flooding on a scale no battleship was ever designed to survive. The critical moment comes at 1400. List reaches 35 degrees. This is the point where stability becomes irreversible. Water flooding the lower decks shifts to the low side, creating additional downward force. Yamato begins rolling faster. At 14:02, Yamato capsizes completely. The massive battleship rolls to port until she's upside down, her hull exposed to the sky. Men in the water watch in horror as the ship that was supposed to be unsinkable reveals her red-painted bottom. For 2 minutes, she floats inverted, held up by trapped air in the remaining sealed compartments. Then the forward magazine detonates, either from fires reaching the powder storage or from seawater hitting hot metal. The explosion is visible from 200 miles away, creating a mushroom cloud that rises 6,000 meters. Yamato breaks apart and sinks, taking 2,498 men with her. Only 276 survive. American pilots returning to their carriers report the kill but express confusion at how long Yamato remained afloat. Commander Hugh Winters, leading the Hornet Strike Group, later stated, "We hit her with everything we had. That ship should have gone down after the first 6 torpedoes. She just kept absorbing punishment. I've never seen anything like it." The prevailing belief was that Japanese damage control was exceptionally competent, keeping a doomed ship fighting far longer than expected. The post-war investigation began in August 1945. Commander Edmund Taylor led a U.S. Naval Technical Mission team tasked with understanding Japanese naval technology. When they reviewed captured construction documents for Yamato at Kure Arsenal, they expected to find conventional battleship designs scaled up. What they found was the most sophisticated underwater protection system ever attempted, and evidence it had failed catastrophically in ways the designers never anticipated. The critical discovery came when Taylor's team examined surviving armor plate sections recovered from the seabed. The junction between upper and lower belts showed fracture patterns inconsistent with simple torpedo damage. These were stress fractures, cracks that propagated along rivet lines and weld seams, indicating structural failure rather than explosive penetration. Taylor brought in metallurgists from the Bureau of Ships to analyze the failures. Dr. Robert Palmer, a structural engineer specializing in armor design, examined cross-sections of the junction zone. He immediately noticed the backing plate discontinuity. The gap meant load paths were interrupted, creating stress concentration at unsupported edges. Palmer calculated that a 400 kilograms explosive charge detonating against properly supported armor would produce stress distributed across multiple square meters. The same charge against unsupported armor concentrated stress into a few linear meters, enough to exceed VH steel's fracture threshold. Palmer's report to the Navy Department was unambiguous. The Japanese designed an underwater protection system theoretically capable of defeating any torpedo in service during World War II. However, a construction defect, missing backing plate support at the armor belt junction, created failure points that negated the system's effectiveness. Each torpedo hit did not merely flood design damage zones. It fractured the structural armor, creating breaches far larger than the torpedo itself could produce. In effect, the armor's brittleness, intended to defeat shell penetration, became a liability against underwater explosion. The investigation team wanted to know why Japanese inspectors hadn't caught the defect. They interviewed surviving Kure Arsenal workers, including master shipwright Yamato, who had made the fateful decision to shorten the backing plates. Yamato, now 66 and living in Hiroshima's ruins, explained through a translator, "We were building something unprecedented. The schedule was impossible. Every day brought new challenges. The backing plate installation was difficult. The curves didn't align perfectly. Shortening them by 30 centimeters solved a fitment problem. I believed the visible structure would carry the load." Taylor's team asked why the design specified Class A inspection for the junction but the defect passed unnoticed. The answer revealed a systemic failure in quality control under wartime pressure. Class A inspection meant visual examination and measurement of visible components, rivet alignment, plate thickness, surface finish. But the backing plates, once covered by outer armor, became invisible. The inspection checklist didn't require measuring backing plate length before concealment because the assumption was that installed components matched specifications. Nobody verified because nobody imagined a supervisor would deviate from design drawings. Yamamoto's decision wasn't malicious or negligent by normal construction standards. He was solving a practical problem using judgment accumulated over decades. In peacetime construction, such a deviation would trigger engineering review, structural analysis, and either approval or rejection based on calculations. But Yamato's construction occurred under extreme secrecy and impossible deadlines. The normal checks and balances didn't function. Workers made field decisions that seemed reasonable and never filtered up to designers who could evaluate structural implications. The Americans found this fascinating from an engineering perspective but also sobering. Similar pressures existed in U.S. shipyards building Iowa-class battleships at high speed. American construction practices included more redundant inspections and documentation, but the possibility of similar hidden defects couldn't be dismissed. The Bureau of Ships immediately ordered reviews of armor belt junction construction on all U.S. capital ships, particularly focusing on backing plate installation and support continuity. The investigation also revealed what Yamato's protection system might have achieved without the construction flaw. Tests conducted on intact sections of the torpedo bulge showed the multi-layer defense working exactly as designed. A 600-pound charge detonated against a properly supported section produced flooding limited to 2 compartments, the design intent. The system wasn't theoretical fantasy. It was genuine engineering achievement undermined by a single point of failure. Dr. Palmer calculated that if the backing plates had been installed to specification, Yamato might have survived 8 to 10 torpedo hits without catastrophic flooding. She would still have been damaged, still eventually sunk by the massive air attack, but the timeline would have extended significantly. The rapid capsizing that occurred was directly attributable to the junction failures, creating flooding rates that exceeded design parameters by factors of 10. This raised a haunting question. How many ships throughout history sank due to hidden construction defects rather than combat damage exceeding design limits? Warships were extraordinarily complex, with thousands of workers installing millions of components over years of construction. Quality control caught obvious errors: missing rivets, misaligned plates, incorrect materials. But subtle deviations that looked acceptable to installers but violated structural principles could hide in plain sight. The U.S. Navy incorporated lessons from Yamato's failure into post-war construction standards. New inspection protocols required photographing all structural components before concealment. Backing plate installations received mandatory dimensional verification with results recorded in construction logs. Supervisors lost authority to approve field modifications without engineering review, regardless of schedule pressure. These changes slowed construction but eliminated the possibility of hidden structural compromises. Chief Naval Constructor Keiji Fukuda survived the war and learned of the investigation findings in 1947. He was 64, retired, his life's masterwork destroyed not by superior American engineering but by 30 centimeters of missing backing plate. In correspondence with American investigators, Fukuda acknowledged that the armor belt junction represented his design's most challenging aspect. He wrote, "I understood the junction required special attention and specified rigorous inspection, but I did not account for the possibility that installed components might deviate from drawings without detection. This was my failure as designer, not anticipating that construction reality might diverge from design intent in ways invisible to normal inspection." I created a structure whose integrity depended on perfection I could not guarantee. This admission reveals the central tragedy of Yamato. The ship represented the absolute pinnacle of what 1930s naval architecture could achieve. The largest guns, thickest armor, most sophisticated protection systems. Every aspect of the design was optimized to an extraordinary degree. Yet that optimization created brittleness. The armor was so hard it fractured under stress it wasn't designed for. The protection system was so tightly integrated that a single point of failure compromised entire sections. The construction was so complex that quality control couldn't verify everything. American battleship design philosophy differed fundamentally. U.S. ships prioritized damage tolerance over maximum protection, armor that bent rather than shattered, protection systems with redundancy rather than optimization, construction with verification at every stage. Iowa-class battleships were less heavily armored than Yamato but survived similar punishment because their systems degraded gracefully rather than failing catastrophically. Modern naval architecture has internalized these lessons. Warship designs explicitly account for construction tolerances, assuming components will deviate from specifications within certain ranges. Structural analysis includes failure mode evaluation, what happens when individual components fail, not just how they perform when perfect. Quality control emphasizes verification of hidden components specifically because hidden defects are the most dangerous. Yamato's wreck lies at 30 degrees 43 minutes north, 128 degrees 4 minutes east in 345 meters of water. Expeditions in 1985 and 1999 photographed the remains. The hull shows massive fractures along the armor belt junction, exactly where Palmer's analysis predicted. The multi-layer torpedo protection system, theoretically the most advanced ever built, sits intact in sections where junction failures didn't occur. Testament to engineering brilliance undermined by construction compromise. The battleship's legacy is complex. She represented Japan's finest engineering achievement and the strategic bankruptcy that wasted resources on obsolete weapon systems. She demonstrated that maximum protection can create minimum survivability if optimization eliminates resilience. She proved that the most dangerous defects are those that look perfect from outside. Master shipwright Yamamoto died in 1967 at age 88. He carried guilt for that 30-centimeter decision for 22 years, the knowledge that his practical judgment contributed to 2,498 deaths. In his final interview, Yamamoto said, "I made warships for 35 years. Yamato was the most beautiful. I believed I understood how to build ships that would survive combat. I was wrong. The ocean taught me that perfect-looking construction can hide fatal flaws. I wish I had torn everything out and started over when I couldn't fit those backing plates correctly. But schedules and shame and confidence in my own experience blinded me." The untold story of Yamato isn't her size or her guns. It's how the world's most sophisticated anti-torpedo system was defeated by 30 centimeters of missing backing plate that nobody knew was missing until American torpedoes found the weakness. Engineering perfection destroyed by construction reality. Invisible compromise making inevitable catastrophe. That's the lesson written in Yamato's wreckage. In complex systems, what you can't see will kill you faster than what you can.